All right, so we talked yesterday briefly about simplifying radicals. We're going to go and do a practice on that after lunch. So if you still feel a little unclear on how that works, we're going to do a practice on it after lunch. But for number 7, for example, when you simplify a radical, you want to break this. Well, we can't do it right away, right? Because 32 is not a what? Perfect square. So we want to basically break it down into factors, but we want one of the factors to be a perfect square, right? So what can you break 32 down into?
8 times 4.
You could do 8 times 4, so we can do it that way. All right, which one of those is a perfect square? 4. What's the square root of 4? 2. So then 2 goes on the outside, and then what's left inside?
8.
Only that's not done yet, right? Because what else can you break 8 down into? So I can break that into 4 and 2 also. Which one of these is a perfect square? 4, so that gives me what? So I've got 2 times 2 on the outside, which is what? 4. So that's where you got 4 root 2. If you're using your calculator to do that and don't know how to actually do it, you cannot use your calculator on that part of the quiz. So it's not going to be very helpful if you don't know how to do that, okay? So I understand your calculator can do that, but if you don't know how, that's not going to be helpful. So you can do it that way, or what I would do is I would say, what's another way to get 32? And it's 16 times 2. Which is a lot less steps. But that does require that you be able to see that 16 times 2 gives you 32. So you just start to get used to it. The more you do it, the more you start to see the bigger perfect squares that can go into it. So say, for instance, you had something like 75. What are the perfect squares that go into 75? No. You can break 75 down into something. 15 would work, but 15 is not a perfect square, so 25, yeah. So you'd break it down to 25 times 3, and then what's the square root of 25? So you end up with 5 root 3. And again, this is the kind of stuff that just comes with practice. Like I look at that right away and I'm like, oh, 25. But I've also been doing this for 20 years. 15 years? When did I take Algebra 1? 14 years? I don't know. That's for a long time, okay? So that comes with practice. Just like when we first started factoring and you had to figure out what multiplies to this that adds to this, and at first it took a lot of thinking, and now you can probably do it a lot faster. The more you practice this, the easier it gets, okay? So what we're going to talk about today is adding, subtracting, multiplying, and dividing. It's a lot of stuff, but the rules are really similar to what you've seen before. So honestly, I think today's lesson is a lot easier than yesterday's lesson. Okay, so when you are adding radical expressions or subtracting them, just like when you have a fraction and you have to have like denominators, or when you're adding together like terms, what does it mean for a term to be a like term? Has to have something in common. So say, for instance, I said 7x plus 8y. Can you add that together? No, because one of them has an x and the other has a y. So you couldn't add them together. Same thing with radicals. They have to have the same radicand. And remember from yesterday, the radicand is the what? The stuff where? The radicand is inside the house. So what's inside the house? So in this case, what are my radicands? 5 and 5. So are those like? Yes. Then we could add them together. Okay? Are these like? No? Why not? This one doesn't even have a radicand, right? So they're not like terms, so you cannot add them together. When they are like terms, you just add together basically the coefficients, so the stuff outside the house. So this is 2 root 5 plus 4 root 5, which gives you what? 6 root 5. What stays the same? The radicand stays the same. So what's inside the radical will stay the same. So if I have 6x minus 2 root x, what would that give us? 4 root x. 6 minus 2 is 4, and the radicand stays the same. Okay? You cannot do it if they are not like terms. So if they aren't like terms, you would just leave it as it is. So for instance, if I gave you this problem, could you do anything? No, they're not like terms. Okay? So now if I added this, xy and xy, now could you? Yes? And it would give you what? 10 root xy. Okay? Radicand just stays the same. So the addition rules are really similar to what you've already done with variables. If they're like terms, you put them together, but you don't change the term, you just keep the radicand the same. Okay, so what would you get for A? 11 root 7. Good. All right, that's a fully simplified radical, so we're done. What about root B, or what about B? Okay, why is it 8? Yes, even though there's nothing here, just like any coefficient, if there's no number there, what do you assume it is? A 1, so it gives you 8 what?
8
Root y. Good, keep the radicand the same. What about here? You leave it. Why? Yeah, those are not similar radicals, so this is already done. That's as simple as it can get. Okay? So those are already simplified. If you want to just rewrite the answer, you can. Don't put nothing, because then I just think you didn't answer it. Okay? So put something there. All right? I mean, I guess you could put the word nothing, but don't just leave a blank space. Okay? Or you can just rewrite it. 12 root 2 minus 4 root 11. Just don't leave a blank, or I think you didn't do anything. Okay, Brendan?
Could there possibly be an exponent, like 2 exponents on each one, and you still add up?
Can you give me an example?
Like 12 squared root x.
Oh, 12 squared? Okay.
Root x plus 12 squared root x.
Do they have the same radicand? Yes? So then you can do it. What's the answer's radicand going to be? Just x. And then what is this?
12 squared.
Which is 144. And this is? So it would be 288. Okay? Now, if it were like this, could you do it? No. Why not, Matthew?
They're not the same radicand.
They're not the same radicand. Could you simplify this one?
Yeah.
Yeah, because this is a what? Perfect square. What's the square root of x squared? So it moves where? Outside of the house. So then this becomes 12 root x plus just 12x. Because the square root symbol goes away if it simplifies. Okay? Now still, you can't add them together because this one has a radical and this one doesn't. Okay? So simplify as much as you can, but you can't do anything further here because these are not like terms. All right. Sometimes you're going to look at them and think, well, I can't add those together because those are not like radicands. However, are they simplified? Is 12 a simplified radical? No, because you could break 12 down into what? 2 and 6, but neither of those are perfect squares.
4 and 3.
4 and 3. Is one of those a perfect square? Good. So we'll do 4 and 3. And then what about 27?
9 and 3.
9 and 3. And what does 4 give you?
2.
So 2 root 3 plus, what does 9 give you?
3 root 3.
3 root 3. So now what do they have?
Same radicand.
The same radicand. So they are now like terms, which gives you what? 5 root 3. Okay? So if it's possible to simplify the radical, do that first. Because then you might notice that they have something in common. All right. What about B? What about B? Can you simplify these? Can you simplify 8 to what?
4 and 2.
To 4 and 2? And can you simplify 45
Yeah.
to what?
9.
9 and 5? Okay, what happens here? Which one of those is a perfect square?
4.
So that becomes a
2.
2. What do I do with the 2 and the 3 that's already outside?
You got multiply.
Multiply them. This is all multiplication because there is no symbol. So I've got 3 times 2, root 2, which actually gives me,
6.
good, 6 root 2 plus, what is this going to give me? 3 root 5. Are those like terms? No. So can I add them?
No.
Do you have to do this part?
Yeah.
Why?
Because you have to make sure at the end
Yeah, you have to check and see because you might not be able to look at it and see that those are not like terms. I'm looking for the fully simplified answer. Just like you can't leave a fraction like this, what do you have to do to it? Reduce it to 1 over 4, right? So just like you reduce a fraction, think of this like reducing radicals. The difference is instead of reducing by a GCF, we're reducing by the greatest perfect square, okay? So you're looking for the greatest perfect square that goes into it. So when somebody said at the beginning or back in the problem before, 12 was 6 and 2, is that true that 6 times 2 gives you 12? Yes, but why don't you want to use those? Neither one's a perfect square, so it doesn't help you get it out of the radical, okay? All right, what about over here? Can you break down this one at all? No, 7 is not a perfect square. I can't break it down, so I'm going to leave that as it is. What about 28? 4 and 7, and then I still have an x, right? So then that's going to still be minus 7x. What does the 4 give me? 2, and I already have a 5, so that becomes good. So 10, 7x minus 8, 7x, and can I simplify?
Yes.
Yes, why?
7 tables.
Yeah, they match. They match inside the radical, so they're good. So then that gives me what? 2 root 7x. Because does the radicand change in your answer? No. 10 minus 8 is 2, so 2 root 7x. Okay, adding and subtracting tends to be more difficult than multiplying and dividing because there are more rules. All right, just like with fractions, just like with variables in general, there's more rules with adding and subtracting because things have to be alike. So at your boards, do these 8. For the first 4, they should already have like radicands. For the second 4, you might need to simplify. You might not, but you might need to. Okay, go. All right, so with multiplying, the same rules do not apply. You do not need like terms, so you can multiply anything you want together. The rules are just you multiply whatever is outside the radical by whatever else is outside the radical, and whatever is in the radical by whatever is in the radical. So for instance, here, I've got radical 3 times radical 6. Those are both inside the radical, so I multiply them and I get radical 18. Okay? So radical 18 is right here. However, I'm not done because what can I break that into? 9 and radical, which is going to give me 3 root 2. So there's my final answer. Okay? So things that are inside radicals, you can multiply by each other. They do not need to be like terms, but at the end, you still have to do what? Simplify. So just like you would with a fraction where you have to reduce, you've got to simplify the radical so you end up with 3 root 2 in this case. All right, when there is stuff like this where it's squared, what does squared mean? That times itself. So what would this look like if I wrote it out expanded? 5 root 3 times 5 root 3. So I basically just have 2 of them, right? So what do I multiply by each other, do you think? 5 times 5. Why both of those? They're outside the radical, okay? And then that's going to give me 25. And then what else do I multiply? 3 times, which gives me 9. And what's the square root of 9? 3. So it ends up actually being 25 times, which is good. All right, what do I multiply here?
8 and 4.
8 and 4, which gives me, is that inside or outside? Inside. What do I have outside?
2.
Just a 2, and I've got nothing to multiply that by, right? Because there's an imaginary 1, but 2 times 1 is still 1. Okay, 8 times 4 you said is 32. And then what else do I multiply? X times, which is squared. Good. X times x is x squared. So can I simplify this? Can I? Let's just do the number first. Can I break 32 down? Yes. To what? Don't tell me 8 times 4 again, because then we're going to have to do that whole boat again. 16 times 2. Good. All right, so 2, 16, 2, and then x squared. Are any of these perfect squares? 16 and x2. So my answer ends up being 2 is still on the outside. 16 becomes x squared becomes x. And what's still in the house? 2 by itself. I can't break it down anymore, so that's done. And then what do I do with these? And what's 2 times 4? So 8x root 2. All right, so that's my final answer for that one. So we start by multiplying and then we simplify. And all of the simplifying is the stuff that we touched on yesterday, and it's what you're going to practice after lunch. So again, if you're still thinking like, I don't know where this came from, that's what we're going to go over after lunch. But also, can somebody walk me through, just verbalize, what did we do here? Why did I take it from 32 to this, well, it looks kind of like a mess? Do you have a question or do you want to answer mine? Okay, go.
So what you did with 32 was, since 32 is a perfect square.
It is.
It is.
Is it? 36 is a perfect square.
No, since 32 has the multiple of 16.
Oh, so it has a perfect square factor. Okay, got it.
Since 32 has a perfect square factor, then you are able to break it down.
Yeah, good.
Which
Was 16 and 2, right?
Which was 16
Yeah.
and 2, but you can't get rid of that x2 because it just can't leave.
Yeah, it doesn't just disappear, right?
So that's when you do the same operation, but you still add the x2.
Yeah, good. Okay, so you've still got the x2. Why did I say don't pick 8 and 4? Yeah, do 8 and 4 work?
Yeah.
Yes, but then you have to do a whole other step. So again, it's not that 8 and 2 is wrong, it's just 16 and 2 is what? Not better, just more efficient. If you like to take the long winding road, that's fine, okay? Long winding roads in math, though, tend to lead to more mistakes. So the quicker you can get somewhere, the better it is, not only for efficiency, but also because the less chance you have to make little mistakes, the better off you are, okay? So you'll get to know this, like you'll see 32 so often, and you'll just know that it ends up being 16 and 2, okay? You'll just start to see them and you'll get it. All right. So, something like this, distributing. What does distribute mean? Something's outside the parentheses, and then what do you have to do with it? Yeah, it applies to everything inside it by multiplication. So again, we said distributing is like handing out. So basically here, I'm handing out the root 2 to the 5 and the root 12. So I'm going to rewrite this down here. So I've got a root 2, 5 plus root 12. So if I hand it out to here, what does this give me? What do you think? No, it's not root 10. Because where's the 5? In a radical or out? Outside. So it has to stay outside. And then the 2 goes where? Inside. So this ends up actually just being 5 root 2. Just like when you multiply 5 times x, what do you get? 5x. Okay? So think about a radical like a variable. And then when you multiply this, now these are both inside a house. So then what do you get? Radical 24. Good. Can I break any of these down? 24. Can I break 5 root 2 down? No. Good. So I'm just going to leave it alone. So 5 root 2 plus, what does 24 break into? 12 times 2, but I'm not going to use that. Why not? It's not... Yeah, none of those are perfect squares, right? So we'd have to do more work. Okay, so what else could I use? 6 times 4. Is there anything else? 8 times 3, but neither of those are perfect squares either, right? So it seems like 6 and 4 is our best option. All right, you notice that I will always write the 4 first. Why?
The smaller one?
It's not because it's a smaller one. It's the perfect square. That one's the perfect square. Okay, so 5 root 2 plus, what's the square root of 4? 2 root 6. Can I break 6 down anymore?
Yes.
You can, but to what? 3 and 2, which does that really help me? No, because neither of those are perfect squares. So then I will just leave this. I'm done here. All right, if I can't break it down to a perfect square, don't. Okay, so what would you get over here? What am I distributing here? 3 to the 3 and 3 to the... And they're all inside radicals, which means I can multiply all of them. So what does the first one give you? And the second one? Good. Minus root 15. Can I simplify 9?
Yes.
What is that? Can I simplify root 15?
No.
No, why not?
Because that would be a perfect square.
What's the only thing it breaks into? 5 and 3. Are either of those perfect squares?
No.
So we're done. That's it. So 3 minus radical 15. All right, and the last thing we touched on yesterday, we said we cannot have a what in the denominator? You can't have a radical in the denominator. So how did we say you could get rid of a radical 2?
Multiplying it
By radical itself. Multiply it by itself. And if you multiply by itself on the bottom, what do you have to do on the top? Good. Okay. What's radical 2? Radical 2.
2.
Just regular 2, right? It gets rid of the radical. What's radical 7, radical 2?
Radical 14.
Good. Radical 14. Okay. Can I break radical 14 down?
No.
To 7 and 2, but again, does that help me? No? So we're done. Radical 14 over 2. All right. What would I have to multiply by here? Radical 8n and radical 8n. What happens on the bottom? They cancel out, so what do I have left? 8n. Good, so just whatever was in the house is now outside of the house. All right, what am I going to get on top?
You'll get 7 times
56.
56.
56 in.
Radical 56n. So yeah, 7 times 8n. So 7 times 8 is 56, and we still have the n. Now, I'm getting to know this well enough to know what can I probably do with 56. Okay, something probably goes into it. So I want to look at perfect squares. And I know that 4 goes into it. So I'm going to try 4. 4, and then 4 goes into 5 one time, with 1 left over, and 4 goes into 16 4 times. And then radical n over 8n. Okay, which one of these can I break down? 4, which gives me 2. Can you break 14 down?
Yes, but there's no.
Yeah, but not to a perfect square, so we leave it as it is. All right, and then on the bottom we still have 8n. Brendan.
Since 8 goes into 56, wouldn't it be, can it just be 6 in?
Absolutely. No, not 6n. How 6?
Because
8 goes into 56, right? So you could break it down to 8, 7n. But then you'd have to break this down to 4, 2, 7n. Okay, so then this would be 2. Radical 2 times 7 is 14n. So it's the same thing. So that would work, just more steps. All right. Okay, 2 over 8 reduces to what? 1 over 4. If you don't do this part, I'm not going to mark you off. Like if you do all the hard stuff and then just forget that, that's okay. All right, so on your practice ones, just do those.